Hi folks, I'm Mr. Fullerton, and today I want to talk to you about work. Now, we'll start off by defining work, and we'll talk about work in the physics sense, and we'll also calculate the work done by a force. So what is work? You do work on an object when you move it. The rate at which you do work is known as your power output. And when you do work on an object, you transfer energy from one object to another. As I do work in lifting my phone, I give it gravitational potential energy. As I throw it sideways, doing work on it, I give it kinetic energy. So when you do work on an object, you transfer energy from an object to another. Work, in the physics sense, is the process of moving an object by applying a force. If you don't move anything, no work is done. So, some examples of work. A stuntman in a jetpack blasts through the atmosphere, accelerating to higher and higher speeds. The jetpack applies a force, causing it to move. The hot expanding gases are pushed backward out of the jetpack, and by Newton's third law, the reactionary force of the gas pushing the jetpack forward causes a displacement. So the expanding exhaust gas is doing work on the jetpack. There is a force causing an object to move. Work is being done. In another example, a girl struggles to push her stalled car but can't make it move. Although she's expending significant effort, since the car doesn't move, no work is being done. An object has to move in order for work to occur. A third example. A child in a ghost costume carries a bag of Halloween candy across the yard. If the child applies a force upward on the bag, but the bag moves horizontally, the forces of the child's arms on the bag don't cause the displacement. Therefore, no work is being done by the child's arms. The force has to be causing the displacement in order for work to be done. So calculating work. It's a fairly straightforward formula. Work is equal to force times displacement. W, the work done in joules, is also known as a Newton times a meter. Now you'll recall that a Newton is a kilogram meter per second squared times a meter, so a joule is a kilogram meter squared per second squared. A joule is a unit of energy and of work, a Newton times a meter. Force is the force applied in newtons, and d is the object's displacement in meters, or in other courses, if you're using x for displacement, work equals force times displacement x. Now, if only the force in the direction of the displacement counts toward the work done. So when the force and displacement aren't in the same direction, you have to take the component of the force that's in the direction of the displacement. So in this case, if we have a force up and at an angle, but our displacement is sideways, we have to use the component of force in the same direction as the displacement. In this case, we can use our trig to find that would be F cos theta. So the work done in this example would be F cos theta times d. And sometimes you'll see this written as F d cos theta, just rearranging the terms. But it may be helpful to remember F cos theta is really giving you the component of the force in the direction of the object's displacement. Let's see if we can't put this to work. In sample problem 1, an appliance salesman pushes a refrigerator 2 meters across the floor by applying a force of 200 newtons. Find the work done. Well, since the force and the displacement are in the same direction, the angle between them is 0. So work, which is F cos theta d, well, cos theta is going to be cos 0 degrees. The force and displacement are in the same direction. The cosine of 0 is 1, so that's just going to be our initial force times displacement, or 200 newtons times 2 meters, for a total of 400 newton meters, or 400 joules. Very straightforward problem. Complicating things a little bit. A friend's car is stuck on the ice. You push down on the car to provide more friction for the tires by way of increasing the normal force. You push down, the normal force must be greater. That allows the car's tires to propel it forward 5 meters on the less slippery ground. How much work did you do? Well, in this case, the car's displacement is horizontally, but the force you're applying is at a 90-degree angle to that. So the work done is F cos theta times the displacement, or F cos 90 degrees times the displacement. Cosine 90 degrees is 0, therefore the work done will be 0. You did no work because the force that you applied did not cause the displacement. The car caused the displacement. Only the force in the direction of the displacement counts for work. So in this case, you didn't do any work. You expended a lot of energy and were perhaps very helpful for your friend, but no work was done in the physics sense. And another problem. How much work is done in lifting an 8-kilogram box from the floor to a height of 2 meters above the floor? Well, it's easy to see the displacement here is going to be 2 meters vertically. And the force must be applied in the direction of the displacement. You have to push up in order for the box to move up. So that's going to be pretty straightforward. But what force is it that you apply? Well, in order to lift the box, you have to at least match or overcome the force of gravity. Therefore, the force applied is equal to the gravitational force, or the weight of the box, mg. So mg, the weight of the box, is going to be 8 kilograms times 9.8 meters per second squared, which is about 78.5 newtons. Therefore, the work you're doing is going to be force times displacement, which is going to be 78.5 newtons times your displacement of 2 meters. And the cosine of the angle, cosine of 0 is going to be 1 again, so that'll pop right out, which will give you a total of about 157 joules of work. The key here, recognizing the force you have to overcome to lift an object, is the force of gravity on that object, or the object's weight. Let's try another one. Barry and Sydney pull a 30-kilogram wagon with the force of 500 newtons a distance of 20 meters. The force acts at a 30-degree angle to the horizontal. Calculate the work done. Well, in this case, the work done is going to be force times the cosine of the angle between the force and the displacement vector, or 500 newtons, cosine of 30 degrees, times the displacement of 20 meters. Plug all that into my calculator, and I come up with a total amount of work done of 8,660 joules. Don't forget, you need to take the component of the force in the direction of the displacement. The area under a force versus displacement graph can also give you the work done by a force. Consider the situation of a block being pulled across a table with a constant force of 5 newtons over a displacement of 5 meters, and then that force gradually tapers off over the next 5 meters, so that you have a force versus displacement graph that looks just like the one here. Find the work done. Well, to do this, we need to recognize that the work is going to be the area under the graph. And the area, if we look at this red portion, that's a rectangle. So the area is going to be 5 meters times 5 newtons for 25 joules. And over here on the right-hand side, the green area is a triangle. 1/2 base height is going to be 1/2 times our base, 5 meters, times our height of 5 newtons is going to be 12.5 joules. So when we put all this together, the work done is going to be the area of our rectangle plus the area of our triangle. That's going to be 25 joules plus 12.5 joules for a total of 37.5 joules. So you can also do this graphically if you have a force times displacement graph. Last one. A box is wheeled to the right with a varying horizontal force as shown in the graph below. What is the total work done in moving the box 6 meters? Well, once again, work is going to be the area under a force versus displacement or distance graph. So that's going to be the area of our rectangle here plus the area of our triangle. Well, the area of a rectangle, length times width, is going to be 3 meters times its height, 6 newtons, plus the triangle, 1/2 the base, 3 meters, times its height, 6 newtons. 3 times 6 is 18, plus half of 18 is going to give us 27 Newton meters, which is equivalent to 27 joules.